So in this example, we're at this light panel for the Millennium Falcon, and we're given the different currents and voltages through each of these resistors here, and we're also given the resistance of these resistors. However, the battery has stopped supplying power, and so we need BB-8 to give it a jump. Oh no! This bulb just blew out. Oh man, well that means that all these values right here are no good. With a circuit, as soon as you remove a component or you change something or you rewire it, you are going to have to redo the entire circuit, because now the way that the current flows through everything is completely going to change, and it's going to change the voltages as well. Well, let's get to it. So first things first, if this light bulb is blown out, then this entire path right here, you can think of it like a cut in the wire. And so no current is going to go through here. It may as well not even be there. So let's redraw it with it not there. Okay, there we go. So another thing to notice is that, well, this sort of weird angle at which this resistor is drawn, well, all that's going on here is this is just metal wire. And so I can extend this out, or sort of bend this wire, if you would rather think of it that way, to put it over like this, and I'm not really changing anything. So let me go ahead and do that. And so now this looks like something that's much simpler to work with. So again, our EMF, or our power source over here, is 9 volts. And the resistance of each of these light bulbs is 4.5 ohms for every single one. I'll just put R. So notice here, for these two resistors that are in parallel, because they split off like this, to get the equivalent resistance for parallel resistors, what you do is you do 1 over that equivalent resistance is equal to 1 over each of the individual parallel resistors. So 1 over this resistance plus 1 over this resistance, which this is convenient since these resistors have the same value, or these light bulbs have the same resistance, that this denominator is the same. So this is just 2 over the resistance. And so now, if I just take the reciprocal of both sides here, I'm going to get the equivalent resistance is equal to R over 2. Well, R is 4.5 ohms over 2. Chuck that in my calculator. 4.5 over 2, and I'm getting 2.25 ohms. So let's go ahead and point this guy out with orange, because that's what we're replacing these two resistors right here with. So I'll go ahead and redraw the circuit. And it's the R equivalent. Okay, cool. So now we have that, and now notice these two resistors, the original resistor and my new equivalent resistor, are now in series. And so when you want series resistors, all you do is you just add them up. So this is just going to be that resistance plus this resistance. Okay? So that's really just 4.5 plus 2.25 ohms. So if I add that up, let's see what I get. 2.25 plus 4.5, 6.75 ohms. And so all these resistors here can be replaced. Let me redraw the circuit once more. With just one 6.75 ohm resistor. All right, cool. And then the power source over here was still 9 volts. Now, we need to find the current and the voltage across all the resistors. So what we'll do is we'll start working backwards now that we have this very simple circuit with just a battery and one resistor. And so if we look here, Ohm's law tells us that the voltage across a resistor is equal to the current through it times that resistance. Well, first of all, the voltage here, there's only one resistor that we've got. So all the voltage from the battery of 9 volts has got to be dropped across this resistor. Okay, well we have the voltage then, we have the resistance, we just need to find the current. So I can rewrite this as current is equal to voltage over resistance. And so that's going to be 9 volts divided by 6.75 ohms. So when we do that, 9 divided by 6.75, should be getting 1.3 repeating amps. And from here on out, because I get nervous about losing stuff with decimal places, I'm going to be using the fraction, which is 4/3 of an amp. So that's the current going through this resistor right now. Now when we go back up to this diagram, well, the current is going to be the same through each of these, right? Because think of it like water, it's just flowing through this one wire or this one pipe. So wire without quotes, pipe with quotes. So it's just flowing through here. Well, I know the current here is 4/3 of an amp. I know the current here is 4/3 of an amp. What I need to find now is the voltage. The voltage is not necessarily going to be the same here, because remember the voltage across both of these all together is 9 volts. So if we go here, we get the voltage across this right here, so call it V1. I'll do it over here, V1. That's got to be the current, which we have here, 4/3 of an amp, times the resistance. So through this one, that's 4.5 ohms. And so the voltage across this resistor right here, if I throw that in my calculator, that's going to just be 6. So that's nice, that's 6 volts. Now, to find this, we can do the same thing, but one thing really neat is I now know, looking at this is going to be 3 volts. How? Well, because there was only 9 volts to go around. So if we've already lost 6 volts right here, this has got to be 3 volts. If it wasn't, the battery would short out. So let's go ahead and do this way, just to double check it. So voltage across the equivalent resistor here. It's still 4/3 of an amp. The current's the same. The resistance, though, is 2.25. So when we do that, let's see what voltage we get. Drum roll, please. 3 volts. Now what's nice here, this 6 volts, notice when we go back up to this diagram up here, this resistor is not changed. We didn't put that into an equivalent resistor aside from the last one. So that's still going to be 6 volts. We've solved that part. So the resistance is that, the voltage is 6, and the current through this resistor is going to be 4/3 of an amp. Now what about these two? Well, notice that now we do have the voltage. The voltage across each one of these is 3 volts. But what we don't have now is the current. We know that the current altogether through here has got to be 4/3 of an amp because it goes through and flows, but notice it can split. It can go this way and it can go this way. Is it going to split perfectly in half? Maybe, but you can't assume that. So we'll just use Ohm's law once again. We know the voltage is 3 volts, and so now to find the current through this one and this one, say current through 2, that's going to be equal to voltage divided by resistance, so that's 3 volts over 4.5 ohms, volts over ohms, and so that's going to give, write that a little neater, ohms down there. So throw that in, 3 divided by 4.5, and we're getting 0.6 repeating, so 0.6 bar. Whenever I've got repeating stuff, I prefer to use a fraction whenever possible, and so that would be 2/3 of an amp. Now, looking at this is 3 volts divided by 4.5 ohms. So in this case, the currents are equal, but I'm never going to assume that. I'm only going to do this and then double check. If these resistors were different or if the voltage was different somehow, you can't assume that just because the current splits, it splits equally. But in this case, we're good. So that's 2/3 of an amp through both of these. A really good check on your work is, well, we said that 4/3 of an amp has to go through this collectively. Well, 2/3 plus 2/3, 4/3. Likewise, for the voltage, 6 volts is dropped here, 3 volts is dropped over here for a total of 9 volts. And so there we go. We've solved the circuit. We've labeled everything. We've got a 9-volt power source. The resistors for each of these is 4.5 ohms. That's what we started with. Voltage and current here is 6 volts and 4/3 of an amp respectively. and it's 3 volts and 2/3 of an amp through each one of these, respectively. So there we go. Even though the light bulb over here blew out, we were able to solve the rest of it and see it right now. So there we go.